All right, ladies and gentlemen, class recording has started for today. So, yesterday, we started talking a little bit more detail about Schrodinger's model of the atom. And Schrodinger's model of the atom consists of orbitals. So what is an orbital? Eric, good.
It's just where all the electrons are most likely to be.
It's likely places for electrons that surround the nucleus. Let's not go so far as we're saying that it's a region in motion, because just like, and I think I brought this up in the last class, I might not have come up with it for you guys, right? So here, yesterday, we drew this, or we talked about this picture, right? And all of these things that we put on, these spaces that we put on one at a time, are orbitals. Someone in the last class, I think it was the last class, I don't think I was here, asked, well, how many orbitals are there? How far does this go on? And the answer is, technically, they go on forever, that they kind of go on infinitely. But just because the space is there doesn't mean that electrons are always in them, right? We said they are probable locations for electrons. But it also depends on how many electrons there are in your atom and stuff like that. So next week, when we talk about orbital diagrams, we'll talk about, even though these spaces exist, where are electrons actually in them, all right? So, orbitals are probable locations for electrons. Jack, are you give a question?
Yeah.
Okay, good.
So you said the quantum mechanical model,
Yep.
that's the actual model right there?
Well, remember, a model is a representation of something that is too big, too small, too complex for us to observe, right? So, technically, this is a model of the model of the quantum mechanical atom, right? This is a little bit more detailed of a model of the quantum mechanical atom. And today, we're going to talk about how we go from this picture to this picture. So that's a lot of what we're going to do today. Okay. Julie, go ahead.
Can we have to draw a model like that?
No, never drawing. So we'll see. The drawing that we do today and tomorrow is setting the groundwork for next week. That this is too much to represent on a single atom basis, like on every individual atom. You can't draw this for every single individual atom. So we have ways of representing this information shorthand that summarizes what's there, but really gives us the important parts. And we'll talk about that next week when we get into orbital diagrams and stuff like that. Now, Julia, I might ask you something like this, where these are specific kinds of orbitals, and we'll talk about the differences between them. So I might ask you to maybe draw or identify something like on an individual basis, but never like that whole model, like on a test. Okay? All right, are we okay with that for the starters? So, yesterday we introduced the idea of, is my screen freaking out? Yesterday, we introduced the idea of a quantum number, or quantum numbers. What do quantum numbers do for us? Very good.
The address for the...
Like a quote-unquote address for an electron, right? We are looking at this picture, all right, with all of these different orbitals and trying to distinguish all of those orbitals from each other, right? Because they're all separate places. Some are similar to others in color, some are similar to others in shape, but they're all different places. So how do we distinguish one from the other? And that's what our quantum numbers do for us. That idea of an address, right? That each individual location is uniquely identified, that's different from all the other individual locations, like the way that your house has a unique address that's different from every other address at every other house in Westlake. Okay? All right, good there? Okay. We talked about the first quantum number yesterday, and we referred to that as the principal quantum number. And we said that more than anything, the principal quantum number describes what for us? What is the principal? Energy level. Okay? So we start off with low principal quantum numbers, and then we move to higher principal quantum numbers as we move out from those areas. Okay? Or sorry, as we move out from the nucleus. Principal quantum number identifies energy, which identifies generally how far from the nucleus are we. Okay? All right, good with that so far? All right, let's break from this and let's look at something else to try and introduce a concept that I'm going to introduce to you here in a second. Okay? All right. Here is a world map. Okay? And it is a population map, although it's not the best population map in the world because it just has like the population of countries. Hold on one second. Let me do this. I have a better one that I'm going to show you in a second. Say again? Oh, that is not the picture. Oh, there it is. All right. Oh, 1994. Come on, Wikipedia. That's
Whoa.
Memolition. Not sure what that website is, but we'll go with it. All right. Does this get any bigger? Yeah, we'll zoom in. All right. So here is a map that shows the world's population and the population density. Are we familiar with the concept of population density, right? Okay. So we notice some similarities, right? And we notice some differences, okay? So first, well, I'll open it up to the floor, right? So what are some things we notice about population density worldwide? India and China are pretty big, okay? They're very big, right? Eastern part of the U.S., not so much the western part of the U.S., right? Right? Always, not always, but a lot near water, right? Okay, we find more population density near water, and that's western part of the Europe is really, really, really densely populated, but then when we move across, right, to a lot of that Russia area, there's not a whole lot of population density. Nobody in the Sahara Desert, right? Okay. No, not a lot in Australia. Okay. Do we know why there's not a lot in Australia?
Desert.
It's a desert, pretty much, right? Okay. We have population density along the coasts of Australia, but most of Australia is a desert. Okay. All right. So we see some areas, right? Now, if we zoom in, and I won't do this right now because I have a different thing I'll show you, right? This part of China, the eastern part of China, almost all of India is bright red, indicating very high population density. Does that mean that the population in India is evenly distributed within India? No, not necessarily, right? If we were to zoom in, we could see, even within a very densely populated area, differences in population density, right? To illustrate that, all right, let's go a little more close to home. Okay, so here, I zoomed in. Here is a map of the United States. Okay, on the United States map of the population density, or on the world map we looked at, right, you could tell that there are certain areas of the United States that are more densely populated than others. And when we look at it on a state-by-state basis, we also see that as well. Even in the eastern half of the United States, right, which looks really densely populated on a map, like West Virginia is in the eastern part of the United States, but it's not real densely populated, right? North Carolina, Virginia, Pennsylvania, New York, right? Pretty densely populated in that area. But let's zoom in a little closer to home, right? So now I'm going to take this over on the side here, and I'm going to take it from the national level to a county level. So we'll look at different counties. Okay? This is from the U.S. Census in 2010, so obviously things have changed. There's Nebraska, right? Nebraska is not very densely populated at all, okay? But even within Nebraska, that doesn't look densely populated on a map. Well, that's Kansas, my bad, sorry. I really do know the difference between Nebraska and Kansas, right? But even within a state like Kansas that is not densely populated on the national map, there are some areas that are fairly densely populated, right? Like Kansas City, basically, okay? So let's scoot over here. Let's go to Ohio, because we probably know that one the best. Okay, so there's Ohio. Ohio looks pretty densely populated on the big map, but when we zoom in, right, we definitely see that there are areas of greater population than other areas, okay? So that's by county, but I'm going to break it down to county subdivision, which is a little bit more detailed. All right, so let's zoom in here. Okay. So, we see that within Ohio, there are areas that are more densely populated than others, right? There's basically 3 areas of big population. Those 3 areas are what? Cleveland, Columbus, and Cincinnati, right? Okay, you know, we have, this is Cincinnati down here, right? This dark area here. Columbus is right in the middle. Here's Cleveland up here, right? This is, anybody, that's Dayton, okay? Up here, it says Toledo right there, right? Here, we've got Akron, Canton in this area right here, right? But, Chris, like you said, down in this area, right, there's nothing there, right? Because do we know what's down there?
No. Farms.
That's not farms, actually.
Coal mines.
That's like the Hocking Hills area. Like, that's forest, and we start getting into not mountains, but like the foothills of the Allegheny Mountains, so a little bit higher population. But then out here, right? Okay, what's out there?
Nothing.
That's farms, right? That's when we start getting close to Indiana, and that's when we start getting into farmland and stuff like that, okay? So, let's zoom in close to home, right? And we go to Cleveland, okay? And I'm going to take this here to census tract. Alright. Okay. Let's zoom in. No, it's not good. Okay, let's zoom over here, okay? So, Cleveland looks pretty densely populated on a map of Ohio, but when you zoom into actual Cleveland, right, there are areas within the city of Cleveland or the greater Cleveland area that are really light yellow, okay? Let's zoom in a little bit more here. All right, so there's the greater Cleveland area. Okay.
Those are cities.
What?
What are those blocks?
The blocks are like divisions within the county where they take census data, basically. So.
Oh, we have 2015.
Say again? We only take a census every 10 years. So 2010 was the most recent census we took of the United States. So that's why. That's what the 2010 census. All right, but even within Cleveland, we see there are places within Cleveland that are not very densely populated, right? When you get down here into Independence and Brecksville, we have like these like really light spots here. Does anybody know what that is?
Big small towns.
No. That's the Cuyahoga Valley National Park, right? So if you've ever gone like skiing at Boston Mills or Brandywine or somewhere along there, right? Nobody lives in the national park, so there's not a whole lot of population density. But if you come over here to like Rocky River, Westlake, right, North Homestead, these are all different parts of those cities, okay? Or even when you get out here into Avon, right, the population density is pretty great because that's where a lot of people live, and a lot of people live very closely. So even if we look at something that's very densely populated on a map, when we zoom in, we see within those even densely populated areas, there are variations, okay? So, taking that back to this model, Schrodinger's model of the atom, we see that starting in the middle, there is a real densely populated area close to the nucleus, which we would expect. But then we see there's a little break, and then there's another densely populated area, and then a break, and then another densely populated area. Similar to Bohr's model, right, in that there's like, you know, electrons, no electrons, electrons, no electrons, but like we said, they're not defined in certain places. But what we do find out is, if we were to zoom in on these densely populated areas, we would find that they're not evenly populated with electrons. That even in these main principal energy levels, okay, if I use that term, does that sort of make sense, right? Even within these principal energy levels, there are areas of more certainty and less certainty. Okay? So, before we get more detailed into the picture, let's talk about those areas of certainty and uncertainty. Okay? And let's talk about energy sublevels. So, within each principal energy level, areas of greater electron density do exist, and we call those sublevels. Just like if we look at a map of Cleveland, there are areas of greater population density and lesser population density. What do we call the areas of greater population density that surround a city?
Suburbs.
Suburbs, right?
Yeah.
Suburbs have greater population density than downtown Cleveland. People don't live in downtown Cleveland. More people are starting to live back in downtown Cleveland, but for the most part, not a lot of people live downtown. The population density is greater in the suburbs. Same thing is true in these orbitals that surround the nucleus. That there are greater greater electron densities within these bigger areas. Okay? And we give these different areas names. So the first sublevel in each principal energy level, that's PEL because I didn't want to write it out every single time, we call the s orbital. Okay? So, that being said, let's go here. Let's start here. Okay, so here's my nucleus. All right? Let's watch in progression. Right? Actually, I'm going to go up here. Okay. So let's watch in progression. Ready? Okay, here we go. Okay? So we said yesterday that our principal energy levels on this diagram are represented by what? What shows us the principal energy levels? Color, right? Every time a new color shows up, what's the first thing that shows up in that new color? A circle, which actually isn't a circle, it's actually what? A sphere, but right, it's a circle, okay? So, that circle, the first circle in each color, the first thing in each color that shows up is the first sublevel. Okay? Therefore, what's true about the shape of that first sublevel? Sammy, it's what shape? It's spherical. And we refer to those first sublevels as s orbitals. So s orbitals all look like spheres. Sometimes they're close to the nucleus, sometimes they're farther out from the nucleus, but they're all spherical. Okay? Good with that? All right. So hold on a second. Before we start writing or drawing, let's do this part here, and then hopefully it'll make a little more sense. Okay. All right. So the first sublevel is an s orbital. Okay. Here we go. All right. So we start here. Okay. S sublevel. S sublevel. It's another ring out, but it is an s orbital because it's a shape. Okay? Now, after this, what shows up? They're not really ovals. What did we say they look more like?
Spheres.
They look more like
Infinity symbol?
figure eights or infinity symbols if you turn a figure eight. Okay, so here, it looks a little more like this in reality. Here. So it looks a little more like this, okay? But for the clarity in the picture, I kind of drew it that way, okay? So this is another sublevel. We refer to this as the p sublevel. Any orbital in the p sublevel is going to look figure eight-ish, okay? But, as we discussed, we can have a figure eight that runs horizontally, or we can have a figure eight that runs vertically, front to back. Okay? All of these are p orbitals. Together, they make up the p sublevel. Okay? Good for starters?
Yes.
Okay, so going back to our outline. The first sublevel in each principal energy level is called S. The second sublevel is called P. Okay? But the first principal energy level doesn't have a P. Why? Because what did we say about that first principal energy level?
Nucleus.
Is it very big?
Nucleus.
No.
No, it's real close to the nucleus, all right? So,
What's
p orbitals always look like figure eights.
What's P equal?
Hold on a second. I'll give you p equal in a second. Okay. Let's talk about these sublevels first. Then we'll talk about how we distinguish them from one another. Okay. So these three down here on the left, these individually are all p orbitals. Okay. P along the y-axis, p along the x-axis, p along the z-axis. Okay, which they labeled a little differently than we labeled ours, but that's okay. It doesn't really matter. Okay. Together, they make the p sublevel. Okay? Are we okay with that idea? Right? If we think about it, taking it back to our population density, right? Rocky River, Westlake, and Bay Village individually are all suburbs. Together, they make up the west side. Does that make sense? Okay. Not those aren't the only cities on the west side, but right, that's sort of how this fits together. Okay? All right. The next sublevel that shows up is called the D sublevel. Remember yesterday, we introduced these ideas of ones that sort of look like an X. Those are our D sublevels. But just like P sublevels don't show up until the second principal energy level, the first time we saw an X shape wasn't until we got to blue, right? Does that make sense from our picture?
Yeah.
So the D sublevels don't start until the third principal energy level. And then finally, there's a fourth sublevel we call the F sublevel, but F sublevels aren't going to start until we get to the fourth principal energy level. So in our picture, green. I didn't show you any of those Fs because they're too hard to draw. Okay? So the sublevel talks about the shape of the orbitals. Okay? We distinguish them with something we call the angular momentum quantum number, which is about halfway down on the back page. We use the lowercase letter L to represent the angular momentum quantum number.
Does that have to be like that?
I do it that way just to distinguish between L and 1. You know what I'm saying? So like, you know, if you...
Indicates the sublevel.
And this indicates the sublevel, which relates to the shape of those orbitals. Okay?
How many numbers are in the address?
4. So we've got 2 so far. All right. So if you go back to the outline that we've been working on, okay. If you go back to the front page of the outline, down at the bottom. All right. Roman numeral number 4, energy sublevels. Okay. Within each principal energy level, areas of greater electron density. The first level is called S. All principal energy levels have an s orbital. Every time we switch color, we start with a sphere, regardless of where it is. The L value that we use for an s orbital is equal to 0. Regardless of where it is, which color it is, the L value is 0. Okay? The next sublevel is P. we use an L value equal to 1 to represent the p orbital. So I think that's at the top of the second page. Okay. L is equal to 1 for p orbitals. Then for d orbitals, L is equal to 2. And then for f orbitals, L is equal to 3. And that's all summarized right below that chart. Okay? All right. Good so far.
So we haven't talked about F yet.
We haven't talked about F yet, and we're going to not spend a whole lot of time talking about F because they're pretty complex and hard to draw, and they don't show up until we get to some pretty big atoms. So, okay. All right. Good there?
Yeah. Okay,
so let's talk about how these things work in our big picture. Okay. Nucleus. First color means this is the first principal energy level. Okay? So, let's say, and this is not going to show up very well, so I'll use black, okay? Let's say we have, that's terrible. Let's say we have an electron that exists in this orbital. Okay? We said that quantum numbers distinguish this orbital from all the other orbitals. Okay? So, this is the first color that we came across, meaning this is the first principal energy level. Okay? So to start our address, right, I'm going to draw this arrow over here, I'm going to bring it over here. Okay? The first quantum number that we use to start describing this location is the principal quantum number, N. Which principal energy level is this electron in?
1.
It's the first one, right? So in this case here, N is going to be equal to 1. Because it's the first energy level closest to the nucleus we can get. Okay? Good for starters? All right. Based on this shape, we now know that this is called what kind of an orbital, or what shape of an orbital is it. This is a spherical orbital, and that means it's an s orbital. Okay? And that means the angular momentum quantum number for an s orbital is equal to 0. Okay?
Should we be drawing this?
Okay, so now this might be a good time when we start like drawing some things. Okay? So why don't we start, actually you can do it however you want to. I would recommend, because we're going to look, the next picture I'm going to look at is the red ones by themselves. So if you want to separate the first, this is the first principal energy level. And if you want to make one of the smaller ones the second principal energy level, that might work for you. Okay? Or you could put the first and second one all together on one graph. That's fine too. Okay? So I would recommend draw this first sphere. Okay? Now, I would say draw this first sphere on the big picture, but then one of your small axes too. Okay? That's fine. You know, I mean, like the big picture, like Julia, the big picture is going to be kind of like the big complex picture that I've drawn up on the top, and that's okay. So, like where you are, like Julia, where you are right now, that you're probably pretty good. Okay.
Should we draw the address too?
We are going to continue. I'm going to continue to do this, so yeah, that will help you identify those things. So yeah, it might be a good idea for you to do like I've done, and maybe draw an electron in there and draw a little arrow to show that that's where we're going. Okay. All right. Good for starters.
Yeah.
Okay. Let's move out one. Let's talk about my red sphere. Okay? And let's say we have an electron. Go away. Let's say we have an electron right there in that red sphere. Okay. We change colors. And we said that that relates to the energy level, or the principal energy level. Okay? So now, this electron, what are we going to do with our principal quantum number? It has to do what?
Go up.
N equals 2. It goes up because we've moved out from the nucleus. Okay? So N equals 2. Okay? But even though we're out a ring, what kind of orbital is this? What
Same.
shape of an orbital is it?
S.
It's still an s orbital. Yes, it's out a little bit further, but it's still an s orbital. And that means the angular momentum quantum number for this one would have to be what? 0.
0.
So now we have two orbitals, and we can tell them apart because they have a different principal energy or principal quantum number, even though the angular momentum quantum number is the same. Alec, go ahead.
Are we going to use the small thing for anything?
If you want to look at individual like colors on the small ones, you can. Although how you draw this picture is totally up to you. Okay.
So this big one, we just keep going.
Okay. So yeah, you can just keep drawing what I've drawn on the big one. Okay. All right. Does that make sense so far? Good so far? Okay. The next thing I added was some ovals, or some figure eights.
Yeah.
Okay? Now, one thing hasn't changed though, right?
The color.
What hasn't changed?
The color.
Color hasn't changed. Okay? Meaning,
This gracious stuff.
okay. Alright? So if we were to describe an electron in that orbital, because it's the same color, it's in the same principal energy level. The energy is similar to that previous one. So that means that N for this electron is going to have to still be equal to what? 2.
Yeah.
But we are in a different type of orbital, right? What type of orbital are we in now? A p orbital. And if you look at your outline, right, the angular momentum quantum number for a p orbital is equal to 1. Okay? Good so far? But remember, in this energy level, there are actually 3 p orbitals. One that goes horizontally, one that goes vertically, and one that goes front-back. So here, if we had this electron, the one we just did, we've already established that there's that, right? But let's say we have another electron here. If we started putting together quantum numbers for that electron, remember, this is a different orbital, right? We have to describe this one differently. It's still in which energy level?
Second one.
Still in the second energy level. It's still red. So N for this one is going to be equal to 2. What type of an orbital is it in?
P.
It's still a p orbital.
Yeah.
Meaning that its angular momentum quantum number
One.
is 1. How are we looking so far?
The same.
The exact same. So there has to be a way for us to distinguish between this one, and this one. And that's where we'll pick it up tomorrow.
Aw.
Okay?
Dang it, man.
I was starting to understand it.